Using computers to draw space curves. So space curves are inherently more difficult to draw by hand than plane curves. For an accurate representation, we need to use technology, and plane curves is pretty much like on the same plane. Like this one here is on the same plane. So that intersection right there is still on this plane. But now if you want to draw some advanced setups right here, we're going to need a computer. So we're going to need to use technologies. For instance, the figure below shows a computer-generated graph of the curve with parametric equations x equals to 4 plus sine 20t, and then all of that times by cosine t, and then the y is equal to 4 plus sine 20t, then all of that times by sine t, and then the z is equal to cosine 20t. So you're going to get a vortex right here, a toroidal spiral, or just a toroidal spiral vortex, etc. there. So that's an amazing shape there. So it's called a toroidal spiral, because it lies on a torus. So it's on a torus and it spirals. Another interesting curve is called the trefoil knot, with equations right here. X equals to cosine, 2 plus cosine 1 plus 1.5t times by cosine t, all of that times by cosine t, and then y is equal to 2 plus cosine 1.5t, and then all of that times by sine t, and z is equal to sine of 1.5t. So it looks a crazy shape like this, a trefoil knot. So here are the graphs in GeoGebra, and so what you could do is just plug that in. You could write a curve right here. So curve, and then you can also indicate right here the parameter. So I put the x, y, and z components, put with the parameter t, and then you indicate how much the domain of t. So I put t is from 0 to 4 pi. This one's 0 to 2 pi. Again, I just do it until something lines up, until it does a full loop. So here it is, both of them graphed like that. So it's pretty amazing stuff here. So here's the full graph. You can hide them, and you can put that like that. Anyways, that's GeoGebra. So I'll move this away like that. So here's the shape. It's a pretty calculating intensive. And if you go upwards like that, look at that perfect perfect shape on top there. But then from an angle, it does not look like that. So look at that. It looks all out of whack. But now you can see this perfect triangle, three-sided shape, and then there's the sinusoidal waves going up and down, back and forth, but in a spiral. So amazing stuff. And there's the 3D. There's sideways. You can see them all different shapes and stuff. So again, all these links you can go and view them and so on. Absolutely amazing stuff here. So that is quite amazing. So even with a computer, even when a computer is used to draw a space curve, optical illusions make it difficult to get a good impression of what the curve really looks like. This is especially true in the trefoil, not this one right here. So from the top view, it looks pretty cool. So this is especially true in the trefoil, not above. See exercise 3 when I go dive into it deeply. And the next example shows how to cope with this problem. This is called, and this brings us to example 7, the twisted cubic. All right, and this one states, use a computer to draw the curve with vector equation r of t is equal to t for the x, and then t squared, and then t cubed for the y and z components respectively. This curve is called a twisted cube. Interesting. So a solution, we start by using the computer to plot the curves with parametric equations. First, I'll just use my calculus book, the graphs, and then I'll go over to GeoGebra. So the result is shown in, this one here. We're going to plot these parametric equations. X equals to t, y equals t squared, and z is equal to t cubed for t is between -2 and 2. So it looks something like this. So the result is shown in the figure below, but it's hard to see the true nature of the curve from the graph alone. So yeah, it's hard to see if it's all in the same plane, and it looks like it's curving up a tiny bit there. Yeah, this one, it does look like it's going up there, but this looks a bit flat. So again, it's hard to tell what if this is a complex shape or just simple one. So most three-dimensional computer graphing programs allow the user to enclose a curve or a surface in a box instead of displaying the coordinate axis. So you could put a box like this. So when we look at the same curve in a box as in the figure below, we have a much clearer picture of it. Yeah, this one right here. So this is actually a box where this goes to the corner, and this goes to the bottom, the rectangular box there. So it looks like it's literally going from a twisted cube like that all the way up from the one corner to the other corner. Like that. So that's pretty cool stuff. So we can see that it climbs from the lower corner of the box in the upper corner nearest us, and it twists as it climbs. Yeah, so it twists right here as it climbs. So it's a twisted cube there. We can get an even better idea of the curve when we view it from different vantage points. The figure below shows the result of of rotating the box to give it another viewpoint. So if you rotate it, looks like this, and it curls up like that. It's a pretty cool setup there. And now this figure, the figure below, or the figures below, show the views we get when we look directly at a face of the box. So this is looking at it directly from the top. So directly from the top is just a parabola. And then if you look at from the side view, it looks like it's a cubic setup there. It's going like this and up. And then looking at the side view, it looks like a inverted parabola, convex parabola like that. From the this is the side with the Z and Y. This one, this was the front view. This is looking at it directly in the front. So that means looking at it from this face. That face looks like that. If you look at it directly from this one, you get the cubic setup there. That's the this is the XZ. So that's the XZ, and then looking at it from the top, you get this parabola. So the top right here, or the bottom. And that's just the XY. There's the XY. Just pretty cool stuff. So in particular, the top view shows the view from directly above the box. It is here, just fix that up. It is the projection of the curve on the XY plane, namely the parabola y equals x squared. And yeah, that is pretty much because number t is x and y is t squared. So in other words, y is equal to, well, x squared. The side view shows a projection on the xz plane, the cubic curve z equals x cubed, because again, z is equal to t cubed, while x is equal to, and I'll just write that for completeness. So we have z is equal to t cubed, but we know that x equals to t. So in other words, this equals to x cubed. So yeah, so that's the projection on it, is just a cubic function, like that. And similar for this parabola. So it's now obvious why the given curve is called a twisted cube. So here it is, and just without the box. There it is with the box like that. This is all the views in one place, and there's a different vantage point. And there's the top, there's the front, and there's the side view. Or actually, yeah, no, this one is, yeah, this is the front view. This is the front. That's the side. This is the top. Yes, I think so. So views of the twisted cubic. And here's a graph in GeoGebra right now. I'll open this up. So open that up while it's opening. We'll go back here. So twisted cubic, you can just put that in again. I just made it from a -10 to 10. The other one is a -2 to 2, but yeah, I could have just done that. But anyways, I made it from -10 to 10. And it goes like that. It goes all the way up. And this is the top view, side view, front view. Yeah, like that. And the exact sides there, I didn't bother making them perfectly aligned, and so on. So if we go back into here, so it should load up. So there's the curve. So you can play around with it. So yes, as good as a box is, but having an actual 3D and then moving it around. Because again, my comics book is a bit old, so they probably didn't have this ability. So there it is. That's pretty cool stuff. So again, you can look at it and so on. Oh, actually, it probably did have this, but again, it's a book. So putting this in 3D as a book, and there it is. It looks pretty fascinating. It doesn't look that much of a cube. It looks more like a twisted knot, just a knot. It looks like a knot. All right. So that's pretty cool. And continue further. So another method of visualizing a space curve is to draw it on a surface. And here what I did was I put this header right here just to make it a bit neater. So visualizing space curves on surfaces. So another method of visualizing a space curve is to draw it on a surface. For instance, the twisted cubic in example 7 lies on the parabola y equals x squared. So, because again, in the vertical setup, this is the vertical one, it is a parabola. So it's literally on the parabola from this xy on the vertical side. So if we were to draw it on, the curve is actually on the surface, which is a parabola. So it's on this. So if we can see this when we eliminate the parameter t from the first two parametric equations. So x equals to t and y equals to t squared. So if you eliminate it, what ends up happening is we'll just plug in t inside here. You get y is equal to x squared. Yeah, so that just ends up like that. The figure below, and when you have y equals x squared, that means, well, z could be anything. It doesn't matter what z is. It's gonna, in other words, z is infinite up and down. It's just gonna have a surface, just similar to that cylinder we had. So the figure below shows a cylinder and the twisted cubic, and we see that the curve moves upward from the origin along the surface of the cylinder. So in other words, that twisted cubic, it's literally just going, it starts off from here. Yeah, it starts off from, where does that go? It starts off from here and goes all the way up. Yeah. So there it is. Yeah, this part right here. And goes all the way back up there. So fascinating stuff there, indeed. And it's always on that there. We also use this method in example 4 to visualize the helix lying on the circular cylinder. So we already showed that over here. And a third method for visualizing the twisted cubic is to realize that it also lies on the cylinder z equals to x cubed. So this is apparently considered a cylinder, even though it's like a cubic cylinder. So when you have z equals x cubed, we have this cubic setup here as again the y could be infinite all across. So what ends up happening is it's on it, but it's also on, so it's also on then all the way over to the other side, but it's also on the parabola. So in other words, it's on both of them. So it could be viewed as the curve of intersection of the cylinders y equals x squared and z equals x cubed. But again, this views a cylinder. This is a parabolic cylinder, and this is a cubic cylinder. Again, they call those both cylinder. I double checked, and they're right. So, so again, that's what my calculus book calls this a cylinder. I just call it surface. So anyways, so let's graph this in GeoGebra to see this a bit better. So here's a twisted cubic. There's a cylinder with cylinder 1 is y equals x squared. That's a parabolic cylinder. And this one is cylinder 2. That's a cubic cylinder. Z equals x cubed. So first I draw this strictly on the parabolic cylinder, and then this one is on the cubic one. And notice it's on it. And if you put the intersection, it's perfectly on. It's actually quite amazing. So again, this is the epicness of mathematics. Let's continue back here. And the mathematics, you can see the same thing in different ways and basically validate. Okay, this one didn't show up there. I do not know why it did not show up there. Cylinder 1. Okay, so I think it didn't save. So I'm going to have to do it right now quickly. And we'll do that right now. Cylinder 1 is cylinder, let's go write this down here. Cylinder 1, and then this is y equals x squared. Like that. Cylinder 2. Z equals to also x squared, and x cubed, cubed, yeah. And there it is. I'm gonna save this so that it saves it. No, I thought I saved it. So there it is. That's absolutely epic stuff. So we're gonna unhide this, and look, it's on it. And I'm gonna close this a bit just so we can see it better. Yeah, so it's literally on it. So absolutely amazing stuff. It's on the other one by itself, and it's on both. And now it's at the exact intersection. So that's crazy stuff there. That's amazing stuff. All right, there we go. All right, epic stuff there, and there's the all the curves.